Hi, I'm Emma Cave. I am a Clean Energy Institute graduate fellow here at the University of Washington in the chemistry department in Professor Cody Schlenker's group. So today I'll be showing you how to test a battery Coincell using the MACCOR battery testing system. This is a pivotal piece of equipment that the battery researchers here at the University of Washington use. This one is located in CEI's research training testbed. So before we look at the software for the MACCOR battery testing system, let's go over what materials are required for testing, as well as some information you'll need to know before you begin programming. So you'll need your electrode with your active material loaded on it. In my case, I will be using a graphite negative electrode on a copper substrate. This electrode will be placed in a Coincell with this sort of configuration and crimped. So our final product that we will be testing is this Coincell shown here. For video tutorials of these procedures, please see the links in the description below, as a few of my CEI colleagues have already made very nice videos going over how to make an electrode and a Coincell. So before we program our procedure into the MACCOR, there are three things that we will need to know ahead of time. First, we'll need to determine what C rate we would like to test our batteries at, or our Coincell at. And the C rate is defined as the rate at which a battery is discharged or charged relative to its maximum capacity. So for instance, a C rate of 1 C means that a full charge or discharge cycle occurs over the course of 1 hour. Going a little faster, 2C rate would be 1 hour divided by 2, which is 30 minutes. And likewise, C over 5 would correspond to 5 hours, while C over 10 would correspond to 10 hours. So it's good to note here that the first cycle that we program into our test procedure is always at a slower rate to allow for stable formation of the solid electrolyte interphase, or SEI. In the case of graphite that I'll be showing you today, I will use a C over 10 rate for the SEI formation, but if you are cycling alloying materials such as silicon or germanium, you would want to go at a slower rate of about C over 20 to allow for this stable SEI formation. So the next piece of information we need to know is the voltage range over which we will sweep. So this is the chosen voltage sweep that corresponds to the battery discharge or charge that is based on the reference electrode in the Coincell. So for instance, today I'll be cycling a lithium-ion battery, so my reference is a lithium metal, and therefore I would like to sweep over a range of 0.01 volts to 1.5 volts. If you were for instance, using sodium metal as your reference electrode for a sodium-ion battery, you would want this reference voltage range to be referenced to sodium rather than lithium. So the last piece of information we need is the applied current that we will choose. So this is calculated based on the specific capacity of the active material, the mass of the active material, and the desired C rate that we have chosen from above. So I'm going to go over a little bit about how to calculate this applied current based on the information that you'll have going into your testing. So how do we calculate this applied current that we will program into the MACCOR? So we will know the weight of our electrode. We should know the weight of the copper substrate, the electrode composition. So in our case, this is 90% graphite, which is our active material, with 10% binder, and the theoretical specific capacity of graphite, which is 372 milliamp hours per gram. So the first step is to calculate your active material weight. So to do this, you subtract the weight of your copper substrate from the weight of your electrode and multiply it by the percent of active material. So in our case, this gets us 3.69 milligrams. The next step is to convert your specific capacity to or to convert specific capacity using your active material weight. So if our theoretical specific capacity of graphite is 372 milliamp hours per gram, we can multiply that by our active material weight and get a current of 1.7 or 37 milliamp hours. And finally, for our cycle, we will calculate the current for the desired C rate that we would like. So for our first cycle of the SEI formation of C/10, that's 1 cycle per 10 hours multiplied by 1.37 milliamp hours, which gets us 0.137 milliamps, or 0.000137 amps. So this number is what we will enter into our program to allow for the correct C rate that we would like, taking into account the weight of our active material. Likewise, the same is done using for the C/5 cycling that we will cycle after the SEI formation, and that is for 1 cycle per 5 hours. And you notice that for that one, we are applying a larger current to drive the charging at a faster rate. Okay, so the first thing we want to do when we come onto the computer is check to make sure that we're aware of which channels are being actively used. So you'll see in state, if they are being currently cycled, it will say active. So we want to just make sure that we aren't going to touch those on the software and on the machine itself, because we don't want to disturb any cycling that's going on currently and mess up someone's samples. So to start here, we want to make our own procedure for how we're going to cycle the battery now that we have the information that we need. So to do that, we're going to click on this button, which is the Build Test Procedure Editor. And it's good practice, usually once you have your procedure written, just to bring up an old procedure and edit that. But for right now, I'm going to show you how to write your own new procedure from scratch. So we'll do new. Okay, so the first step is always to do a rest step, which basically allows your Coincell to reach equilibrium at open circuit potential, or OCP. And we want this rest step to be for 1 hour. So it'll say rest, and your step time will be 1 hour. Oops, that's 10. Hold on. Okay, so 1 hour, and the step time for this, step time just means what's the interval at which data will be taken. The step time for this will set to 10 minutes because we don't need a ton of data for the equilibrium. Okay, so that's our first step. Next, we want to program our SEI formation, or our solid electrolyte interface formation, which will be our slow charging rate that we talked about, or our slow C rate, I guess, that we talked about in the beginning. So to do this, since I'm working with a negative electrode of graphite, I'm going to start with discharge first and then do a charge cycle. This kind of is counterintuitive, but the discharge means that we're lithiating or inserting lithium into the graphite electrode, and the charge cycle is going to be the delithiation process. So where now the lithium is going out of the intercalated graphite. So that's sort of counterintuitive, but make sure to keep track of that. And so the mode we will select is current. So we're going to program in the calculated current for the correct C rate that we have just talked about. So for this will be our C rate of C/10. And we calculated that to be 0.000137. And the thing to note here is to make sure that you limit your sig figs to only 3 for this value, or for any value for that matter, because otherwise it will cause an error in the system and you won't be able to start your battery run, or your testing run. So I'm going to discharge or lithiate and charge or delithiate at the same rate. So I can just copy and paste this into that cell. Limit will stay the same, or sorry, will stay blank, value will stay blank. And the end type, we want to program in our voltage range that we want. So both of these will be voltage. The operation here is that we want this to be we want this to stop once the voltage reaches less than or equal to 0.01 volts, like we talked about in the intro, as our range. For the charge or delithiation, we want the voltage to, we want this to stop once the voltage reaches greater than or equal to 1.5. So again, this was the range we talked about in the beginning. And we will copy and paste this step time. So we want these step times to record now every 10 seconds rather than every 10 minutes, so that it gives us a good data set to work with. So I can copy and paste this into here. Okay, so this is our first C/10 lithiation, or I guess battery cycling for our SEI formation. So once this is done, we want to tell the program to now move on to our next step of cycling. So to do that, in step 4 under type, I will go down to do 1, which basically just prompts it to start this next set of steps. So the next set of steps will be identical to the SEI formation, except this time now we're going to be cycling over a C/5 rate rather than C/10. Oops. So let's just select this line, copy it and paste it in there. We'll select this line and copy it, paste it in here. And now we want to make sure that we change the voltage or the current that we're going to apply based on our calculations we did in the beginning. So now we want our applied current to be 0.000274, like we calculated for our C/5 rate. And again, we're going to do that for both the discharge and charge cycle. So for the C/5 rate, we want to track how the Coincell cycles over time. So in order to do that, we're going to loop this cycle. So we're basically going to have this cycle for 50 times. So to do that, we, in step 7 under type, we'll go down to loop 1. And that will come up with this loop count equals, and then we just enter in the amount of cycles that we want to have. So that could be 25 if we wanted to cycle for 25, or 50 in our case. And that will be it. So then to finish it off, we'll command it to end. So the last line will we will go down to end, and that's our program. One other thing to note in here, if you want to delete a line, if you mess something up, so say I accidentally pressed that and I want to delete this line, you just right click and right click on this step and then press delete step. So that'll delete the whole line and you can start over again. And you can always copy and paste lines from up here if you need to. So I'll make sure to reset it to end. And the last thing that we will do is, this is just helpful for yourself, is to enter a description of what we programmed in here. So this is a graphite electrode with a C/10 SEI formation and a C/5 for 50 cycles. So that way we'll be able to easily find this again. So we want to save this procedure, so we'll go File, Save. And usually you can just save it right into this procedure folder that pops up automatically. And you want to save it in a way that will be easiest to find. So the typical file name is initials underscore the date, so 1905-07. The active material, so that's graphite in our case. The mass of the active material, because we'll need that for data analysis after the fact, so 3.69 milligrams. And I will just write cycle test, just for my own knowledge that I'm doing a cycle test, okay? So we'll save that. Now our file has been saved, and we can press OK. If you want to check the syntax of your code, you can press this green check, and that should come up with this syntax check complete and no errors found. If there are any errors, it should point those out for you in this page. Okay, so the procedure is done. So now it's time to cycle our battery. So again, like I said in the beginning, we want to make sure that we're not going to touch any of these channels that say active on them. So we want to look down in this state column for a channel that is available. So channel 25 looks good, which is available. So before I do, well, okay, so channel 25 is available. So what I want to do here is double click until this says selected. So this is perfect. We want to make sure this says selected. And now we can go up here to this green play button, or it says start test, and press that. And now in this window, we want to scroll down and find our procedure that we just made. So it should have your initials in the beginning. Here we go. So this is the procedure that I just created. So you want to select your procedure, and then you want to enter a valid file name. So usually the file name should be similar to the procedure that you just wrote. So what I'm going to do is just copy this and paste it into here so that I know the active material, the date at which I did it, and the weight of the active material. And in the comments section, you can write any comments you may have about conditions of your electrodes or anything of the sort. So to load your Coincell, you'll want the top. Well, you have two sides basically. One has the larger flat side, and one is the smaller side that you want to be facing the instrument. So we want the larger flat side to be facing out, and we'll just click this into this sample holder. Just double check that it's all connected correctly. And now we'll take this over to the instrument and plug it into channel 25. So all of the channels are written on here. So it's very straightforward. All of these are set up so that you can just plug this right in to channel 25. And again, when you do this, make sure that you don't touch any of those Coincells that are being actively cycled. You can see that the ones that are being cycled right now have tape on them saying do not disturb, so we want to make sure that we don't touch those at all. Okay, so now that that is in and looks good, all you need to do is come back here and press start, and that will begin your test, right? So now we're in the resting cycle for 1 hour, and then we'll begin to cycle our battery. So once the test has gotten going, once the cycling has begun, and once it's finished, you can select your channel and come up here to this graph icon, and that will bring up a plot of the data that you're collecting. So I haven't collected any data yet, so it won't show here. But what this gives us is a plot of voltage as a function of time, and on the bottom is capacity as a function of cycle number. So once the data set starts to begin to collect, this will start populating, and when it's finished, we can go up to options and view data from chart. And this will be populated now once the cycling is done. So this will be time in hours, voltage in volts, and current in amps, or in amperes, I guess. And this will be your important data set that you want to save as a text file, and then bring back to your own data processing software to do your data analysis. So to do that, you go to File, Save as Text, and then you'll save it as a text and import it into your own system. And we'll go over a little bit of the data that you can collect using this technique next. So now that we've seen how to cycle our battery on the MACCOR, let's go over a little bit about data processing after the fact. So I showed you a little bit on the instrument how to save your data using the chart, but I'm going to show you a little bit about how to use the view data from file. So we'll do the same procedure, click the graph icon, go to options at the top, and click view data from file rather than view data from chart. So when you view data from file, that will give you all of the data that was collected for that specific run, or for your cycling profile that you've programmed. And then to save this, go to File and Save as Text. So from this data, there's a column that will give you capacity and show you your cycle number. So using the active material mass and the capacity from the data file, you can now calculate the specific capacity and then compare that to your theoretical specific capacity using two different types of plots. So the first plot is the specific capacity that you've calculated from the column of capacity divided by the weight of your active material. And you can plot this as a function of cycle number that is also given in this view data from file file. And this is just a representative plot over the first 25 cycles of the 50 cycle run that we programmed. And as you can see, the specific capacity stays pretty consistent over the course of 25 cycles. It's interesting to note that this first data point is higher than all of the rest of them, and this is due to that formation of the solid electrolyte interphase during the first cycle. And again, we did this at a slower rate so that this layer can be produced in a stable manner, so that in the case of graphite, it stays pretty stable and consistent after the fact. So another common piece of information that we usually get from this plot is then normalizing to your cycle number 2 for this to track your capacity retention. So that's basically just seeing how your capacity proceeds over time. So in this data set, again, the benefits of graphite is that its capacity retention is quite good. So you can see over the course of 25 cycles, it stays pretty much consistently at 1, which indicates that no fade has happened in the capacity over time. So these are a couple of examples of data plots that you can get from the information from the MACCOR
battery testing system. There are many more to explore.
So today we have cycled a battery on the MACCOR battery testing system. We've programmed our own cycling tests, loaded our Coincell onto the instrument and started the test, and exported our data for further data analysis. I hope this video was helpful, and happy battery cycling.